take you through, hopefully, a series of slides that are going to introduce to you the observational evidence of us living in a remarkably old, by human lifespan standards, old universe. And hopefully what I'm going to be able to do is actually show you some of the tools that scientists have used to establish these ages. And with a lot of science, you can actually begin asking these questions and approaching these questions by doing some very simple exercises. So, for example, if you want to know the age of the universe, you can simply ask the question, what is the oldest thing that I can find around me? Because simple logic would say the universe has to be older than that, right? I don't think anyone's going to have a stretch of their cerebral cortex in understanding that piece of logic, right? So I can first ask if anybody in this room witnessed the birth of the universe. There's always one. So I could be rude and I could make an estimate of the oldest person in this room, but I bet that there's nobody here that's willing to argue with me that the universe is younger than, say, 21 years old. Right? So we can ask these very simple questions and we can have a little bit of fun starting off, but then we can simply look around us and look for objects that are old. Okay? So the first thing we can do is look around for artifacts left by previous generations of humans and see if we can place a date on them. All right? So as an example here, we have one of the oldest known pieces of writing by humans. This is a Sumerian cuneiform. Cuneiform means wedge-shaped, and you can tell why just simply by the style in which this record has been made. So simply what the Sumerians doing, they were the culture living in Mesopotamia about 5,000 years ago. That's what's now known as Iraq, in between the Euphrates and Tigris rivers. What they were simply doing was taking reed and simply making impressions in clay to get this record. Has anyone got any idea of what this is a record of? You do? Probably taxes. Well, depending on your point of view, you're slightly right. So this symbol down here is widely regarded as the head of a human and a bowl. So this is the Sumerian symbol for ration. These little strikes here are actually numbers. So this is a record of rationing corresponding to some number. So up at the top left here, you'll notice that there is a large pot-looking symbol. This is the Sumerian symbol for beer. This is a record of beer rations for workers.
So there is progress.
Yeah. Now this has actually been dated back to 5,300 years. All right, and we'll actually go through the methods that people have used for dating these artifacts in a moment. But this is relatively recent. 5,300 years is by no means stretching the ages that we can find of objects that have been left by humans. Okay? So moving on to a second example. This is a set of pictures of a small trinket. This is only about 2 or 3 centimeters tall in real units, of a piece of jewelry carved out of a mammoth tusk. And this was found in a cave in southern Germany. Now I'm going to butcher the pronunciation, but it's Höhlefels, the place where this was found. And this artifact is known as the Venus of Höhlefels, and it has been dated to 35,000 years ago. Okay? So you'll notice that this is a piece of jewelry. There's actually a little tab on the top here for some person to pass a little bit of string through and wear it around their neck. So we've actually got evidence of some very old artifacts. This is actually one of the oldest known artifacts of art, jewelry, that we have found so far. Now we can take things even further. We can look around for bone records of Homo sapiens. So on the left here is a photograph of two sets of remains found of Homo sapiens. It was found in Ethiopia, and these remains have been dated back to almost 200,000 years. So these are the oldest known human remains. So already in just asking simple questions like what is the oldest thing we can find, we have already established that the universe is going to be much older than the objects that we have found around us. That's going to get annoying. All right. So the method for determining how old something is that we have found is based on a technique known as radiometric dating. Scientists have a really irritating way of using complex phrases to describe fairly simple processes. And here is another example. What's happening in the diagram, it seems fairly complicated, but those of you that have done some introductory physics may have come across the processes via which radioactivity occurs. So we've got three examples here of how radioactivity can occur. On the left, we have what's known as alpha radiation. This is where one particular element has decided that it has got too much energy, and it would rather much be in a lower energy state. This is why you are all sitting down right now, right? You would rather be in a low energy state. So the uranium in this case is worked out that actually if it gets rid of a helium atom, it can be in a lower energy state, and there it prefers to stay. In some other examples, we have, for example, here the carbon-14 atom releasing an electron and becoming nitrogen-14. We also have over here an example of gamma radiation, whereby an excited particle will actually release a photon. Now these particles are doing this, as I said, because they prefer to be in a lower energy state. So actually to describe radiometric dating, what I've tried to do is to come up with an analogy. All right? When I was a lot younger, one of the first books I read that got me interested in astronomy and astrophysics was Hawking's Brief History of Time. And he is very good in that book of coming up with analogies to describe fairly complex situations. And my favorite is the two-dimensional dog. Those of you that have read the book will remember the graphic of a two-dimensional dog. A two-dimensional dog has got a really big biological problem in that if it has a hole at one end for food to go in and a hole at the other end for food to go out, how does the top half of its body not separate from the bottom half of its body? So with a very simple analogy, Hawking used a fairly straightforward little mind exercise to demonstrate the difficulties of their actually having the existence of two-dimensional beings. The example was being, how can we as three-dimensional beings appreciate a four-dimensional space? Okay? So I've tried to come up with an analogy here for radiometric dating. And what I've used is the melting of ice. So instead of uranium turning into thorium, for example, via the emission of helium, we've got ice decaying into water. All right? This is not in real time, for those of you that haven't figured it out yet. So what we've got is two scales displaying the mass in grams of whatever material is on them. They were set to 0 when the little little containers were placed on them. So what you are looking at is 5.6 grams of ice with a little bit of uncertainty about how this transitional water is being counted. And over on the right, you have 2.7 to 2.8, it's going up, grams of water. So we're seeing how the ratio of ice to water is changing as a function of time. So this is sped up, of course. These are actually displaying minutes on the far left. So we're watching the melting of ice. Ice is being used in this case as an analogy for radiometric decay. Now, there are going to be significant differences between how this actually occurs and how radiometric decay occurs. And I know that this ends at 50, so I know I've got plenty of time to explain this. Right? And there's another one a little bit later as well. So this is also a good exercise in seeing how uncertain you can be before you actually get a fairly good idea of how much ice compared to water there is as a function of time. All right? So if we can model this somehow, then I can come up, or we can come up with an expression, a mathematical expression that will allow us simply to look at the ratio between ice and water and work out how much time has passed since the ice was first put there. Okay? This is the fun bit where it disappears. Now you get to worry about, oh, what happens to the water that's on here? You'll actually, the scales that we've used are actually for measuring gunpowder. All right, so they're highly sensitive. And in the next one, I'll actually show you, you can detect the water evaporating. Okay, a plot. Uh-oh. All this plot shows is time in minutes going left to right and the mass in grams on either scale. So the line that is declining to the right is the amount of mass that was left in ice as a function of time. And the line that is increasing to the right is the amount of water that was on the scale. You'll notice that if you add these two numbers together, you would get a straight line across the top telling you what the total mass was at any time. You will notice that the two curves cross in the middle at about the half time that it takes for the whole of the ice to disappear. So immediately, just from plotting how much mass was on the left scale versus the right scale, I can come up with what's known as the half-life of this melting ice. All right? Now, some of you may be thinking, well, you started off with 7 odd grams of ice. If you started off with a smaller amount of ice, you'll get different results. Okay, well, let's have a look at that. Let's have a look at a smaller amount of ice to start off with. So before we started with 7 odd grams of ice, now we've started with 3.2 grams of ice, and this one's been colored red. It's just red food dye. When I first did this little exercise, you couldn't see the ice because it's white, right? I was like, I know, food coloring. There you go. So as we watch this block of ice melt, we see the same features that were happening with the blue block of ice melting. Now, this is a little bit different to the process used for radiometric dating. Instead of actually using weighing scales, in radiometric dating, what we are doing is measuring how much mass there is in a particular nuclide of a particular element. All right? We don't use actual mass scales for that. We use an instrument known as a mass spectrometer. So what a mass spectrometer does, it basically heats up the material. So if you take a lump of, say, here you can watch the evaporation. It's that sensitive. See the water evaporating. That would be a way more boring video. So with radiometric dating, instead of there actually being physical scales that actually weigh the amount of material that is in one particular nuclide to another particular nuclide, just the name of the parent and the daughter radioactive material, we've now got a mass spectrometer which is going to ionize, which is just the fancy way of saying removing all of the negative charge from an atom. And now we have an atom with a particular charge, and we have atoms of another particular charge. And when you move those atoms through a magnetic field, they are deflected through that magnetic field. This is how old televisions used to work, by the way. The less massive particle is deflected more, and we can see when those particles hit a detector exactly how much of the lighter material there is compared to the heavier material. So that is the only real difference between watching ice melt and actually using a mass spectrometer to determine the ratio of an element that has decayed into another element, a radionuclide that has decayed into another one. Okay? Now, what we have here now is plotted the data from the melting of the red ice. Yes, it's different, but you'll notice that the gradients of the melting are the same. Okay? So we can fit slopes to this data, all right? And we can measure what that slope is, and we can give it a letter K. And in radiometric dating, K is called the decay constant. You can kind of see decay, never mind. These black lines are actual fits to the data. You'll notice that regardless of the initial mass of the ice, the slopes are the same. So K is the same, and it doesn't matter how much mass we started with. All right? So now we've got these slopes. And you'll notice that the increasing slope is exactly the opposite of the decreasing slope. So now with this data, I've got 4 measures of the decay constant of ice. So now I just need to do a little bit of maths. It's called maths because there's more than one number. So, never put equations in a public lecture. Never mind, broken the rule. This is fairly easy, right? Instead of writing the mass of 2, which is the mass of water, compared to the mass of 1, I'm just going to give that the letter R for ratio. And instead of writing the mass of 1 plus the mass of 2, the total mass, I'm just going to give it the letter big M. And if I do that and do some simple rearranging, then I can calculate the age of the ice based on simply the total mass, the ratio of the two masses, so the ratio of the amount of water to ice, and the total mass. So I can now go back to that video. I don't even need to now look at the clock. All I need to look at is the ratio of the masses and the total mass, and I can tell you what the clock was saying. Now, this is how we do radiometric dating. But instead of using the ice, we are using radioactive products. All right. Now, here's some examples. Remember that half-life I was telling you about where the two lines crossed? Here are some examples of the half-lives of some familiar elements. So we've got carbon at the top, carbon 11, so it's just got 11, basically 11 units in its nucleus, and that takes 20 minutes to decay. It takes 20 minutes for half of it to decay. Carbon 14 takes 5,700 years. So you'll notice that this is a number that's very useful for dating, for example, that Sumerian cuneiform, or that the Venus of Hula-Fels, right? Because when those objects were made, they will have absorbed a certain amount of carbon-14 that is naturally present in the Earth's atmosphere. So at that point, that object will contain an amount of ice, carbon-14. And as that object ages, that carbon-14 ice is going to change to nitrogen. So we can just measure the ratio of carbon to nitrogen using a mass spectrometer to get the age of that object. Now, it turns out that there are many atoms that are unstable and decay. And the half-life, for example, of chlorine-36 is 300,000 years. And the half-life of uranium-238 is 4.5 billion years. All right? Now, there are a couple of differences between the carbon-14 and the uranium-238 that we're talking about. You'd be quite worried if uranium-238 was just naturally floating around in the Earth's atmosphere. Actually, in some parts of Russia, it still is, right? So there are two types of radioactive particles. There are the radioactive particles that are formed from previous supernova from which our solar system formed. And there are the radionucleotides that form in our own Earth's atmosphere. Now, it turns out that carbon-14 also has a cosmic origin. It's a cosmonucleotide. And this is formed when nitrogen in our upper atmosphere gets bombarded by cosmic rays. So that is when that's how carbon-14 is formed. Okay? So we have cosmonucleotides and primordial nucleotides. So the cosmonucleotides are good for aging things like fossils, and the primordial nucleotides are good for aging things like rock. So now moving forward with these two different types of nucleotides for radiometric dating, we can ask ourselves, now what is the oldest thing that we can find? And it turns out that you're very familiar with the oldest thing that we can actually tell the age of. So using uranium-238 that has been trapped in rock when the Earth was formed, we can get a very good, which means 3 significant figures, age for the Earth. All right? This is an experiment that you can do and verify as long as you have a mass spectrometer. Or you could just think about the ice video. Right? So moving away from the surface of the Earth, let's now talk about some astronomy, right, which is actually what I'm a bit more familiar with. What are the oldest things that we can see in the universe? So this is a star that we're very familiar with, the Sun. And because we are orbiting around it on the Earth, we know the mass of our Sun very well. And we can ask ourselves, why is the Sun bright? And we can try and link the brightness of the Sun to any of the known processes that we have on Earth that make things bright. And this is an exercise that was done several hundred years ago. So first of all, coal, when you set it on fire, is bright. So if we have the Sun made of coal that is burning, how long would the Sun live? It turns out that it's not very long at all. It's only a couple of thousand years. So we then have to ask ourselves, what other processes do we know that can keep this amount of mass burning like this for a long time? And it turns out that that is the fusion of hydrogen. So hydrogen will actually fuse together under the right circumstances, in this case density and temperature, and produce helium. So we can take the mass of our Sun and ask, if this Sun is made entirely of hydrogen, how long will it live? And if we take the ratio of hydrogen to helium, we can actually figure out exactly how long the Sun has been burning for. And it turns out, not very surprisingly, that it's actually slightly longer than the age of the Earth. All right? So we know that the Sun has to be burning through a process of hydrogen fusion. And using those approaches, we come up with an age of the Sun of 4.57 billion years. So we've already established, we haven't done any cosmology yet, right? We've already established that the universe has to be older than 4.57 billion years just by looking for old things. All right? Now, the Sun, by no stretch of the imagination, is not very interesting in terms of stars. There are a lot more interesting stars out there, and we can ask ourselves the same types of questions. How old are the other stars that we can see in the universe? So we can look at a particular cluster of stars. In this case, this is Messier 4. You won't be surprised to find out that this is a Hubble Space Telescope image of it. And contained within this cluster of stars are a lot of white dwarfs. Now, white dwarfs are the very end product of stellar evolution. So if we wait long enough and our sun burns up all of its hydrogen, it's going to give us a little fireworks display. Hopefully we won't be here. It's going to give us a little fireworks display and then cool down to be a white dwarf. And the way a white dwarf cools is very predictable, much in the same way as any piece of iron that got hot cools. We can figure out how long it has been cooling for. And we can get the ages of these white dwarfs in this cluster of stars, and we find that they have to be 12.2 billion years old. The universe contains these stars. It has to be older than this. Okay? So we still haven't done any cosmology. All we've done is a bit of anthropology, a bit of geology, and a bit of stellar astrophysics. And we've already got a good handle on what the age of the universe, the lower limit on the age of the universe has to be. So you can see how we're bringing all different types of sciences together, all to get very consistent results, especially with the age of the Earth and the age of the Sun, right? You're combining geology with astrophysics. All right. So what are the pieces of evidence that we have in terms of the features in the universe itself that tell us that the universe is old, or that tell us the age of the universe? So what we have here is the spectrum of our own sun. All right, you'll notice that it is a rainbow. That's no coincidence. It is a rainbow. It's just a rainbow that's been looked at very carefully. And upon this rainbow, we will see that there are these dark areas. Now, it turns out that these dark areas represent the elements that are present in the atmosphere, the chromosphere of our sun. And we can see these elements by changing the way we view this rainbow. Instead of viewing it in this way, which is very pretty and everybody quite likes it, what we can do is we can actually take that rainbow and we can see how the brightness of that rainbow varies as we move along it. Now you will have noticed that up here it's dark, and down here it's dark, but it doesn't get dark quite so quickly as it does if we go that way. So when we look at the spectrum of our own sun, we see that it gets dark at the blue end and then dark at the red end, but not quite as fast. And if we actually plot exactly how bright the sun is as we go along its spectrum, we see all of these dips. These correspond to all of those dark patches in the solar spectrum, which is the elements present in the sun itself. So when we look at a star, we can see its spectrum, and we can see that for a star like our sun, it's got a very characteristic shape. That shape, first of all, AMO means air mass zero. Now, that's the technical phrase for saying that this doesn't include any of the effects of the Earth's atmosphere in the spectrum. And then the grey thing is the black body spectrum, and we'll come back to that later. So if we take the spectrum of our own sun, we can actually compare that to the spectra of other stars. So the plots are getting more and more boring, right? The type of sun that we have is the type of spectrum that we see over here. But if we look at other types of stars, we'll see that they have different shapes in their spectra, right? Depending on what type of star they are. Now, in a galaxy, we have a collection of stars. So when we look at the spectrum of a galaxy, what we are looking at is all of these spectra added up together. So here we see the spectra of galaxies. So we're seeing the additive effects of all of the different spectra of stars that are present in those galaxies. So you will see that there are the same types of dips that we get in the stellar spectra, except this time they're a little bit wider because those stars are moving around in that galaxy, so each of the absorption features of those stars are actually adding together at slightly different velocities, slightly different speeds. That's why these lines are not as sharp as the other ones. So you will notice that when you look at different galaxies, the positions in wavelength of these features changes. All right? And it turns out that some galaxies, this plot is backwards in terms of color, right? Some galaxies are redshifted. Their spectral features are shifted to the longer wavelengths. And some galaxies are not shifted at all. They are at the same wavelengths that we see the features in our own solar, in our own star, in our own sun's spectrum having. All right? So we can assign a parameter to these galaxies based on the change in the position in wavelength space of these absorption features, of these dips. And we can say that the galaxy, our galaxy, for example, is at a redshift of 0. Because all of the absorption features in the spectrum of this galaxy are exactly where we would expect them to be. And then when we look at another galaxy, we see that the line has shifted. This feature here, you can see it present in all of these spectra. It has shifted somewhat. So we take the change in that wavelength and divide it by what the original wavelength should be, and we call that redshift. So the example galaxy spectra we see here have been redshifted from 0 to 0.05 to 0.1 to 0.15 and finally to 0.2. All right? Now we can use the same basic physics applied to the Doppler shifts in audio frequencies that you experience when an emergency vehicle goes past you. All right, so when it's approaching you, the pitch is higher from that emergency vehicle, and when that vehicle is receding from you, the pitch drops. All right, that's because the wavelengths that you are experiencing are changing because of the speed of that vehicle relative to you. The same thing can be seen for the velocity of these galaxies. So this galaxy is receding from us at a different rate from this galaxy because these lines have been shifted in frequency, shifted in wavelength frequency, same difference. Okay? So why is this interesting? Well, if we look really closely at these galaxies, we can actually find out how far away they are as well. Now, I like to remind my astronomy students that astronomy is the most difficult science because we cannot change the conditions of the system that we are testing. All right? Chemists can come along and they can add more water and they can make things hotter and colder. Biologists can come along and they can do whatever they do to animals. And they can see how their system that they're testing is changing to the environment that that system is presented with. We can't do that in astronomy. All we can do is stare. It's kind of weird. All we can do is stare and see how things change in brightness as a function of time. Do they get brighter, darker as time moves on? And how that object changes as a function of wavelength. Is it brighter in the blue or the red part of the optical spectrum? Now, it turns out that if we know exactly... Well, the other thing is that we can't actually go out and measure the distance to something, right? Nobody's got a tape measure that long. But it turns out if we know the brightness of an object, if we actually know how bright it is intrinsically, which just means how bright it really, really is, then we'll be able to get the distance from it based on how bright we see it. All right? So this projector has got a certain wattage of light bulb, right, that's hitting my head right now. And if I measure exactly how much energy is hitting my head, and I know how bright the bulb, let's get out of there, and I know how bright the bulb is in that projector, I can tell you exactly how far away that projector is. Right? If I place a 100-watt light bulb over one side of the room and measure how bright I see that 100-watt light bulb, I know it's a 100-watt light bulb, and I can tell you how far away I am. So if there are certain types of stars that act as our 100-watt light bulb, and we measure how much energy is coming from those stars, we can tell how far away they are. Now, it turns out that there are a certain class of stars called Cepheid variables. These are stars that are changing their brightness as a function of time. So as we watch them, they are blinking at us, rather much like a lighthouse blinks at us. What is happening in these stars is basically they are expanding, and as they expand, they cool, get dimmer. And as they get dimmer, there is less support against their own gravity from radiation, and they contract again and get hotter and brighter. And they do this breathing. And the speed with which they breathe actually relates directly to their intrinsic brightness. So we can observe these types of Cepheid stars and plot how bright they really are based on their period. So we can watch this time, even if we don't know what the absolute magnitude is here, we can use this plot based on the actual time for them to breathe to get their absolute magnitude. So if we look at these types of Cepheid stars in other galaxies, we will know how far away that galaxy is. There is also another type of standard light bulb or standard candle that we can use. And this is when stars explode, when they end their lives as supernova. So in addition to Cepheid variables, we can look at the absolute brightness as a supernova takes place. All right? The image that we have here on the left is a Hubble Space Telescope image of a supernova that occurred in 1987 in one of the Magellanic Clouds. And we've actually been able to watch how this supernova has evolved through time. Now, when other supernovae go off in other galaxies, we can see how their brightness changes as a function of time, and we can see what their peak brightness is. And it turns out that there's a certain type of supernova whose peak brightness is always the same. Now, because they get very, very bright, we can see these very, very, very far away. And we can use this to establish the absolute distances to galaxies that are very, very far away. Now, you may be wondering why I'm talking about getting the distances to galaxies when we already know how fast they are moving away from us, right? Well, if we look at a galaxy like M100, this is once again another Hubble Space Telescope image, we can see individual stars within this galaxy, and some of these are Cepheid variables. So we get an independent measure to this galaxy based on the distance to it using Cepheid variables, and since 1901, there have been 5 supernovae observed in this galaxy. So in galaxies that are relatively close to us, in this case, 55 million light years away, this is in the closest cluster, large cluster of galaxies called the Virgo cluster, this galaxy, right? We can measure the distance to it using 2 independent methods, overlap the methods, and then use the Cepheid variable distance to calibrate the distance to supernova. And because supernova are so bright, we can see them very, very far away, like a lighthouse, right? So now we've got a way of measuring the velocity that a galaxy is moving away from us at, and the actual distance to that galaxy. Now, this is an exercise that Edwin Hubble did in the 1920s. And ever since then, we have been refining the relationship between how fast a galaxy is moving away from us and how far away that galaxy is. And it turns out that with some precision, these galaxies all fall relatively close to a line that has a slope of 68 this way compared to 1 this way. And we call this number Hubble's constant. So that is 68 kilometers per second. So that's the galaxy moving away at 68 kilometers per second every 1 megaparsec that it gets further away. So a megaparsec is basically 3 million light years away. All right. Now you'll notice that there is some scatter about this relationship, and there are better ways to figure out this number that we'll get to in a moment. But for right now, we can see that the universe, if something is further away from us, it is moving away from us faster. That means the universe is expanding. So we can ask ourselves, what happens if we turn this around? Well, the universe will get smaller. And we're going to come to the point where the universe is going to have basically zero size. So we'll revisit that little note in a moment. But I also want to add another piece of observational evidence that we have to throw into the mix before we can come up with a complete picture of what happened in the universe when it was young. Now, there are a certain type of object known as quasars. Quasars, get ready for this, are supermassive black holes at the centers of galaxies that are gobbling up material. And as they gobble up material, that material gets hot and it glows and it gets very, very bright. Now, because these things are very, very bright, we can see them very, very far away. And when we look at the spectra of these quasars, because they are far away, they are redshifted a lot. So when we look at the spectrum of a quasar, we actually see the quasar light all the way over here in wavelength space. Remember when we looked at the galaxy spectra, we basically had it flat all the way along here and then it went boom, down. Here we've got the quasar peaking up here, so it's at a very high redshift, and in between we see this forest of lines in the spectra. What this forest of lines corresponds to is all of the hydrogen and helium that is in between us and that quasar. So if we are looking at a quasar that's at a very large distance away from us, the light from the quasar comes towards us, and as it does, it passes through all of these clouds of hydrogen. This is just a representation of hydrogen. It's not what it really looks like. And as it does that, that light gets absorbed. So we can see this forest of lines, and that corresponds to how much gas there is along our line of sight to this quasar. And when we measure how much gas there is of hydrogen compared to how much gas there is of helium, we see that there is a ratio of about 3 to 1. There is 3 times much more hydrogen than there is helium. Now, why is this interesting? Well, the only way we know of using stellar evolution through fusion of hydrogen into helium means that the ratio of hydrogen to helium as a result of stellar evolution should be a lot lower than this. So there has to have been some process during the early universe that produced this ratio of hydrogen to helium. So there has to have been a period in the universe's past where hydrogen was fusing into helium a lot. So we've got 2 pieces of evidence here. We've got the expansion of the universe through Hubble's law, which is fairly easy to prove. And we've also got what's known as the cosmic abundance ratio of hydrogen to helium, which is a head-scratcher. Until we realize that not only in the past must the universe have been a lot more dense, but it must also have been a lot more hot. So as the universe gets smaller and hotter, well, remember that we're actually running the universe in reverse. And as we run the clock back, we know that it has to get smaller and hotter. And there's going to come a point when the universe was so hot on average, and that number is around about 3,000 degrees Kelvin, and there's a fairly straightforward piece of physics that you can do to show what that temperature needs to be, at which point no light can actually travel through the universe. So it's a bit like the point of an explosion, where you can see that there's an explosion, but you can't see anything behind it because it's too hot. Any of the light that tries to pass through this explosion basically gets scattered by the fact that it is so hot and dense. So there is predicted to be, and this is nice, right? Before it was observed, there was predicted to have been a signature of a fireball left over from the formation of the universe. Now, because of the fact that it takes time for light to travel to us from a distant object, we can predict that the radiation from that fireball has to be redshifted by a lot. Okay? So instead of the signature of 3,000 degrees Kelvin in temperature, which has a peak wavelength around about, I'm trying to remember, 800 or 900 nanometers, red, that signature from this fireball, the red signature from this fireball, should be redshifted a lot. And it turns out that by accident, the signature left over from this fireball at that redshift was detected using this big horn antenna. And originally the story goes that they really thought that it wasn't a signature from the background radiation left over from the hot, dense past of the universe. And they spent a lot of time cleaning out excrement from pigeons in the actual detector itself. But anywhere they turned this detector, they found a signal, a hissing, kind of a background hissing, like when you tune your radio in between radio channels, you get that hissing. They were getting that in this instrument. And it turns out what they were detecting was that radiation left over from the hot, dense fireball that the universe must have been in the past, based on the fact that we see the expanding universe and the fact that we see a hydrogen to helium ratio that is a lot higher than you can get simply from stellar evolution. So, it turns out that if you want to precisely measure what the temperature of that background radiation is left over from the Big Bang, you need to have a very sensitive instrument, because the peak wavelength of this emission is actually down in the millimeter wave bands. And we need to measure it precisely. So in 1989, there was a spacecraft launched called the Cosmic Background Explorer, COBE, and it determined what the temperature of this background radiation was. There has never been, this is known as a black body spectral energy distribution, which just means how bright it is as we move around in wavelength. There has never been a more accurate fit to a black body spectrum than the one measured from the radiation left over from the hot, dense past fireball of the universe. Right, so this is the actual data, and the red line is the actual fit to the data. And this was done, well, now actually, this is now a long time ago. Right? When you fit what temperature this radiation is, you find a number of 2.74 degrees Kelvin. It should be 3,000 degrees Kelvin. But because it's at such high redshift, it's actually moved all the way back. And we can say that it is at a redshift of 1,100. Now remember when we looked at those near galaxies, those nearby galaxies, they were at a redshift of 0.1. This is a long way away, right? And happened a long time in the past. Okay, so what does this radiation look like? What does that fireball look like? So what we're looking at here is the actual distribution of temperature on the sky from the COBE satellite. If you've ever seen what the map of the Earth looks like when it's kind of splayed out in this kind of oval shape, then this is how they've represented the background radiation left over from the early universe. So you'll notice that it's quite blobby, right? First of all, if we start here and keep moving left, it's like us turning all the way round until we get back to this point, all right? So this is actually 360 degrees across here. So you'll notice that there's definite changes in the temperature as we move across this map. There's a definite cool region here and a definite warm region here. Well, this is very interesting, right? Now, in astronomy, what we like to do is once we have looked at something and got a pretty picture of it, we want to know what it looks like at higher spatial resolution. So a few years later, we launched another spacecraft to look at this same background radiation left over from the early universe, but at higher spatial resolution. So you can flick these two maps back and forth, and you see that there's a definite, you see the hotspot over here is now mottled compared to that hotspot, but it's the same data, right, just at a better spatial resolution. It's like looking through a telescope. So this is the data that we got when we launched the Wilkinson microwave anisotropy probe in 2001. Now, the fact that we see all of these different little mottled regions allows us to do a lot more physics. And this actually allowed us to figure out that the universe, first of all, was at a very young age when this radiation was first emitted, only 380,000 years old. It also showed us that the actual observable matter that we see in the universe, the stars, the galaxy, and the gas, only makes up a tiny fraction of the overall mass energy of the universe. So these observations actually allowed us to determine what the ratio of ordinary matter to so-called dark matter to so-called dark energy was. So you basically look very closely at what the sizes of these little blobs are. All right? So you think that you've got a really good map here until you look at the results from the Planck spacecraft that was launched in 2009. And these are the results from earlier this year. So this is the highest spatial resolution map that we have of the background radiation, the variations in the temperature of the background radiation left over from the fireball that started our universe. All right? And we've actually been able to refine our models of the ratio of ordinary matter to dark energy based on this map, and actually tweaked the age a little bit. We actually made the universe, from these observations, we got a calculation of it being a little bit older. All right? So, how do we actually calculate the age of the universe? That's the title, and this is the last slide. How do you do it? Well, remember Hubble's constant. It's just a question of getting your units right in the Hubble's constant before you get an age of the universe. So Hubble's constant, as we saw before, was 68 kilometers per second per megaparsec. So that describes the expansion of the universe. If we want to turn the clocks back, we want to know about the contraction of the universe, that will give us the age of the universe. And all we need to do is take 1 over Hubble's constant. And this is the first lecture I give in Physics 1, when I'm teaching Physics 1, is get your units right, and you'll find out that physics gets remarkably straightforward if you get them right. So we know that the units for Hubble's constant is kilometers per second per megaparsec. Well, a kilometer is a measure of distance. There are 1,000 meters in a kilometer, and a megaparsec is also a measure of distance. There are 3 times 10 to the 22, a lot of meters in a megaparsec. So if we get everything right, we can cancel out the kilometers to meters, the meters to parsecs, and we can find out exactly what the age of the universe is just based on Hubble's constant. And we find 3 times 10 to the 19 seconds. Well, that's not much good, because everyone likes to prefer to think in years. So first of all, this is the conversion factor to get everything in seconds. We still have to take care of the fact that Hubble's constant is 68. So divide that number by 68, and you end up with 14 billion years. So that is the way we know the age of the universe, simply by inverting Hubble's constant from the expansion that we see. Now, that's the simple way of doing it. The more complex way of doing it is doing a full analysis of exactly how bumpy that cosmic microwave background is. And that's the result, the latest result that came out of the analysis from the data coming from the Planck spacecraft. And when we do that, we get, by the way, to the same number of significant figures, it's the same number, but 13.8 billion years. And this is our best current estimate of the age of the universe. Thank you. Are there any questions? Relevant questions?
Suppose you don't believe in the Big Bang.
Well, you can get into that kind of argument if you want, but I don't think it's really appropriate for this audience, right? Any other questions?
About the uranium-238, you were saying that's how we can tell the age of the Earth.
Mm-hmm.
But wasn't that created in a star? Like, wouldn't that be the age of the star that exploded?
Okay. The question is, if you've got uranium-238, that was created in another supernova explosion before our Earth was formed. Okay. So all we need to do is think about relative error. Okay? So when you look at the half-life of uranium-238, we find that the half-life is 4.5 billion years. It didn't take 4.5 billion years for the solar system to form. At worst, it took a couple of million years. So we can be off by a million years, and we still have a very high level of precision, because you need to get down to 3 or 4 significant figures before you worry about how long it was since that uranium-238 was formed. Yeah, but it's a good question, yeah. Anybody else? Yes, sir?
What's the approximate range on either side of that 13.8? The least it could be, the most it could be?
I would have to look it up, but it's when you quote a number to 3 significant figures, you know that the uncertainty will be on the order of that last significant figure. So it could be plus or minus basically a half a billion years on that order, yeah. So you can still be wrong by a billion years, but it's still an old universe, right? Any other questions? Yes, sir.
Is there any way of knowing how much further it's going to expand and what's going to happen after that?
Okay, the question is about the fate of the universe, and that is one of the questions that we can answer as a result of the data from the Planck spacecraft. So the current consensus is that the universe is what's known as flat. So there's no curvature in the 4th dimension of the universe, and that the universe is going to expand forever and get colder and colder and colder, and it's colloquially known as a heat death. So that is one of the results of the universe. Now this has got some interesting implications, right? If we were on the Earth or on a planet and evolved on a planet that was maybe several billion years older than we are now, we wouldn't be able to build instruments that could actually detect the cosmic microwave background because it would be shifted even further. So we are, in some respects, living in a very, very privileged time in the universe. We are at a point in the universe where we can actually gather the data necessary to actually work out what type of universe we are living in. Yep.
What accounts for the uneven distribution of energy?
Right, okay. So the question is about why is the cosmic microwave background bumpy? Basically, there are small fluctuations very early on in the universe. Remember how we had the picture of the explosion and there was a blob over here? It wasn't a perfectly spherical explosion, right? There were small fluctuations in that explosion. Now, what that means in terms of the amount of energy per unit volume in the universe at that time, there is a little bit more gravity, essentially, in those areas. And what's happening is that area is pulling back the radiation slightly, and that gives it that slight difference in temperature. So what we're seeing, actually, is the early structure of ordinary matter in the universe that then goes on to form superclusters of galaxies, stars, and eventually planets. If the universe was completely smooth, then there would be no little fluctuations in the structure of the universe to allow galaxies to form, to allow stars to collapse. Yep.
How much of the universe have we actually observed the cosmic microwave radiation background? I mean,
This is the entire sky. All right? So this is a projection, this is a two-dimensional projection of the inside of a sphere as we look at it. All right? So this is everywhere. Some people say that the universe is dark, right? It's not if you can actually see in the microwave wavelengths. It looks like this at the microwave wavelengths.
I've always seen, though, that the argument is that Planck's constant can go either way. It's that it's either going to contract or it's not. You know, some say it's cycled through many times. No one knows. You know, so every time I look deeply into the data, it never seems to really be that definitive. You know, I mean, it's possible, but it doesn't.
So the question is about the fine-tuning of the fundamental constants that we see in the universe. All right, so the counterpoint to that is known as the anthropic principle, right? So if they were any different, then the universe wouldn't exist. Can you see how circular this argument becomes immediately? Yeah. Yeah. Yeah.
So you're talking about how the universe, if it infinitely expands and it's going to constantly cool, will it eventually uniformly reach 0 degrees Kelvin everywhere?
Well, if we've got it, if our numbers are just a little bit either way, then there could be a different fate of the universe. So we still need to gather a bit more precise data before we can answer that question precisely.
Okay.
Yeah. Or you could just be really patient and wait and see.
Doesn't the answer have to be no? How could it ever get to absolute zero every place? Where's it going to move the heat to?
Well,
It can't.
what we're talking about here when we look at this plot, right, is that we actually don't understand what most of the universe is.
Well, no, I'm saying it can
Asymptotically, yeah.
approach zero, but it can never get there. It can obviously never get there.
Right, so it's okay when science doesn't know the answer, right? We know what it's not, and we know that it's old. And having an open question like that is what drives scientific discovery, right? So it's okay when you come up with a question that, well, I don't know the answer to, or that we're still working on, right? That's where PhD theses come from. All right, any other questions? I'm kind of dragging this out because I know that there's not going to be any telescope viewing, right? Oh, it's cloudy. You must have seen that already. Yes, sir.
How much wiggle room does this calculation have for variable in expansion rate or variable in cooling rate?
That's kind of related to the question that we've kind of been dancing around already. Yeah, it's kind of like, what does this purple area really mean? Yeah, and we don't know. Yeah. All right, let's have 2 more questions. The cap, yeah.
Is there any possibility that the dark matter that we are talking about, the Higgs boson can account for that dark matter? Is there any possibility of in the future the Higgs boson we recently found? Can that account for that dark matter that we are actually searching for?
Okay, so the question is about relating the Higgs boson to dark matter. The Higgs boson only comes into existence at very, 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 very high energies. Energies that are way above the energies that we see for dark matter. So there are candidates for dark matter particles, and we're trying to figure out what those are right now. There is an experiment running on the space station called AMS that's trying to figure out that very question. Yeah, so open question, yeah. But it's probably not the Higgs boson, right? Yeah.
Another question is, it's like a contradiction question. What is outside the universe?
Okay, so this goes back. So the question is, can you be outside the universe? Could you actually tell me what the universe is?
That's the point I was coming to. It's a like of contradiction. But before the Big Bang, we are supposed to get some kind of particles. Where that particle?
Could you give me the reference to the refereed journal that says that? You are presenting me with stuff that I've never heard of before. So if you could, rather than you trying to tell me stuff that I've never heard of, I can't address a question that I've never heard the source of. Do you understand? Yeah, yeah. So you can speculate whatever you like, right? I can speculate that you are the reincarnated version of Tutankhamun, right? That doesn't mean that you are. We can have these kind of semantic discussions all you like, but it doesn't actually address anything useful. Right? Yeah, they're fun, but they're not going to answer questions like that. All right, one more question. Yeah.
I guess my question is, where and how far are we from the orbit? Do we know from the very center? I mean, if this is all expanding in a circular or spherical way, there's got to be a center, right?
No.
Do we know?
No.
No. Okay.
So the analogy that you can use goes back to what... So the question is, where's the center of the universe? The analogy can be brought back to considering a two-dimensional being living on the surface of a sphere. Right? They don't know that they can go up and down. You don't know that you could go up and down. All right? So there is, in an extra dimension, you could answer that question. But if you were only given the surface of the Earth and you were asked to point at the center of the Earth, you would pick London, England. Because it's at the top of the map in the middle. Right? But it wouldn't actually be the center of the Earth. Right? So when we live in a universe under which we cannot actually physically appreciate the number of dimensions that are in the universe, that is a question that we are asking from a very different point of view about how the real geometry of the universe is. Okay? All right. Thank you very much for coming.